Hello everyone. Today I would like to talk about the gas law calculations. Let's see gas law formulas and sample calculations. Gas law formula. You can see there are different types of gas laws and their formulas. Here when we are focusing on the formula, there are four parameters we need to explain the behavior of the gas. Pressure of the gas, letter P, and volume of the gas, we use the symbol V, and temperature of the gas, uppercase T, and the number of moles, lowercase n. So using those four parameters, we can explain the behavior of the gas. First gas law, you can see Boyle's law. Boyle's law, we relate pressure and the volume. So this number 1, so subscript 1 indicates the initial conditions and the subscript 2 indicate the final condition. At constant temperature with constant number of moles, T and N constant, then the formula for the initial and the final condition is P1 V1 is equal P2 V2. This is the mathematical expression for your calculations. Charles law. Charles law V1 over T1, that is initial conditions, is equal V2 over T2. Gay-Lussac's law. P1 divided by T1 is equal P2 divided by T2. These are the first three gas law: Boyle's law, Charles law, and Gay-Lussac's law. If we combine first three gas laws together, we call combined gas law. Combined gas law formula is P1 V1 divided by T1 is equal final conditions P2 V2 divided by T2. And then Avogadro's law. Avogadro's law relates number of moles to volume. Here the statement is if we increase the number of moles, that increase the volume. Volume and the number of moles is directly proportional. If number of moles increases, volume increases. So N1 divided by V1 is equal N2 divided by V2. Next, ideal gas law. Ideal gas law, PV is equal nRT. P is pressure, V is volume. Pressure times volume is equal, N is number of moles. R is called universal gas constant. You can see the commonly used R value is 0.0821 liter times ATM divided by moles per Kelvin. There are some other R values with different units, but we use this R value for gas law calculations. And T we use Kelvin temperature. So if you have Celsius or Fahrenheit, convert into Kelvin before you apply any kind of gas laws. And next gas law is Dalton's law of partial pressure. Dalton's law of partial pressure explains in a gas mixture, if it contains gas 1, gas 2, gas 3, there are three different types of gases, then the total pressure of the gas mixture is equal the individual pressures. If we add together, we call sum of the individual pressures equal to the P total. Next, under Avogadro's law, we are learning STP conditions. STP meaning is standard temperature and pressure. So here standard temperature we consider 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atm pressure or 760 millimeters of mercury. Under these STP conditions, 1 mole of any gas volume is equal 22.4 liters. Under STP conditions, 1 mole of any gas, 1 mole of oxygen, nitrogen, it doesn't matter the identity of the gas, any gas mole volume is 22.4 liters. This is we call standard molar volume. In addition to these gas laws, you need to understand what is the connection between moles and the molecules. 1 mole of gas, 1 mole of any substance or 1 mole of gas is equal Avogadro number of molecules. So 1 mole of gas equal 6.02 times 10 to the 23 powered gas molecules. With these gas laws and all the other constants, let's go and try to solve some examples. This is the content. These are the questions. There are 6 questions I am trying to solve in this presentation. First question. If 23.5 liter of nitrogen at 728 millimeters of mercury expand to 708 mmHg at constant temperature, what is the new volume? First read the question and then try to understand what is the initial condition, what are the parameters initial, and what are the parameters under final conditions. So let's categorize. First, initial volume is given 23.5 liters. Initial pressure is 728 millimeters of mercury. And this gas mixture expand to new volume. New volume we need to calculate. New pressure is 708 millimeters of mercury. These are the information given in the question. Now if you look at the data given, pressure and the volume. Pressure-volume connection is explained by Boyle's law. Then we need to apply the Boyle's law. P1 V1 is equal P2 V2 for initial and the final conditions. Now let's apply P1 V1 P2 V2 values. Pressure 1 is equal 728 millimeters mercury times V1 is 23.5 is equal P2 708 millimeters of mercury times V2 is the one we need to calculate. So if you divide both sides by 708, right hand side remaining V2 is equal, so after you solve, 24.2 liters. After expand of the initial gas mixture, final volume is 24.2 liters. Second question. A sample of neon gas is held at 25 degrees Celsius and 1 atm pressure. Under these conditions, a gas occupies 5.0 liters. What volume does the gas occupy at 12.5 degrees Celsius and 1.2 atm? So again, let's read the question and try to identify what are the initial conditions, what are the final conditions. Initial conditions, temperature. Initial temperature 25 degrees Celsius. Initial pressure is 1 atm. Initial volume is 5.0 liters. Now this gas mixture inside a cylinder with a movable piston. This gas mixture convert into a final condition. Final temperature is 12.5 degrees Celsius. Final, or you can consider this is new condition. New pressure or final pressure is 1.2 atm. A new volume we don't know yet. We need to calculate. So you can see there are three parameters involved here: temperature, pressure, volume. Just by looking at the parameters, you can see this is combined gas law equation we need to solve for V2. Before we move on to combined gas law, let's convert all the Celsius numbers into Kelvin. 25 degrees Celsius plus 273, it's 298 Kelvin. 12.5 degrees Celsius plus 273, it is 285.5 Kelvin. Now, combined gas law. Let's apply the values. Initial pressure 1 atm times 5 liters divided by 298 Kelvin is equal P2 1.2 atm times V2 we need to calculate, divide by T2 is 285.5 Kelvin. You need to solve this for V2. V2 is equal 4.0 liters. Let's move on to third question. Calculate the number of molecules in a deep breath of air whose volume is 2.25 liters at body temperature 37 degrees Celsius and a pressure of 735 torr. So torr value, let's convert into atm. The connection between atm, or we call atmosphere, and the torr is 1 atm we called 760 torr. So we have 735 torr. If you divide 735 by 760, we can convert into 735 into atm, 0.967 atm. Or you can use the conversion factor as it explained on the slide. Next, let's convert 37 degrees Celsius to Kelvin. 37 plus 273, it's 310 Kelvin. Now our pressure value and the temperature is ready to apply for the equation. Let's apply ideal gas equation. PV is equal nRT. The reason is you need to calculate molecules. To calculate molecules, we need number of moles. So according to the given information, number of moles we can calculate using the ideal gas equation. Pressure and the volume given, universal gas constant value we already know, and temperature value is given. So the only unknown is number of moles. Let's apply the values. Pressure 0.967 atm times volume 2.25 liters is equal number of moles times universal gas constant with units times temperature in Kelvin. So after you solve this, N value is 0.0855 moles. But the question asks about the molecules, not the moles. You will know the connection between moles and the molecules. 1 mole is equal Avogadro number of molecules. Avogadro number is 6.022 times 10 to the 23 power. So 0.0855 moles is equal 5.15 times 10 to the 22 molecules. Let's go to question number 4. A flask contains a mixture of neon and argon. There are 0.25 moles of neon which exert a pressure of 205 millimeters of mercury. If the argon gas exerts a pressure 492 mmHg, what mass of argon is in the flask? So this is related with Dalton's partial pressure law with mole fraction concept. So let's solve steps one by one. There's a gas mixture that contains neon and argon. Individual pressures are given. Partial pressure of neon and partial pressure of argon, then we can calculate total pressure of the gas mixture. Let's add both gases' pressure together. 205 mmHg plus 492 millimeters of mercury, then P total is 697 millimeters of mercury. Now the connection between total pressure and the partial pressure. If we multiply P total times mole fraction, it is equal to partial pressure of argon. The same way, partial pressure of neon is equal P total times mole fraction of neon. So partial pressure of argon is given in the question. It is 492 mmHg. Is equal P total. Pressure total we already calculated 697 mmHg times mole fraction of argon. So after you solve this, we can calculate mole fraction of argon. It is 0.706. Now let's see what is the meaning of mole fraction. Mole fraction is moles of argon divided by total number of moles in the gas mixture. That is argon moles plus neon moles. We already know number of moles of neon present in the flask, that is 0.250 moles, and we know the mole fraction of argon. So let's apply the values to find out number of moles of argon present in the flask. After you solve this, you can get number of moles of argon is equal 0.600 moles. Next, the question asks not the moles, what mass of argon in the flask. If we know the number of moles multiplied by the molar mass of argon converts into mass of the argon. So 0.6 moles times molar mass of argon 39.948 grams per mole, then mass is equal 23.97 grams of argon. Next question. A sample of gas occupies a volume of 9.23 liters at 345 Kelvin and 1.40 atm. What is its volume at 525 Kelvin and 3.20 atm? First, read the question carefully and try to identify what are the initial conditions and what are the final conditions. Initial gas occupies volume 9.23 liter. Initial temperature is 345 Kelvin. Initial pressure 1.40. For this gas mixture converted into a new condition, new volume we need to calculate. New temperature is 525 Kelvin and new pressure 3.20 atm. Now if you look at the parameters given, volume, temperature, pressure, That is combined gas law we need to calculate V2. So let's apply the values for combined gas law. Then you can calculate V2. It is equal to 6.14 liters. Let's go to our last question. This relates STP conditions. Calculate the volume in liters of 124.3 grams of carbon dioxide at STP. Grams of carbon dioxide given. First, we need to convert gram quantity into moles of carbon dioxide using carbon dioxide molar mass. Carbon dioxide molar mass is 44 grams per mole. Any mass value divide by its molar mass convert into number of moles. Mass divided by molar mass gives 2.825 moles of carbon dioxide. Now the connection between moles and the volume. Under STP conditions, standard temperature and the pressure, 1 mole of any gas volume is equal to 22.4 liters. 1 mole volume is 22.4 liters, then 2.825 moles volume is 2.825 times 22.4. If you multiply both numbers together, the volume is 63.28 liters. I hope now you have good practice on how we can use each gas law with the units and correct number of significant figures at the end. Thank you all for watching.